Welcome once again in the class of topology, and in this lecture we will understand what is a net and what are the basic characterizations of a net. So before moving on to the net, in the previous video I have told you what are the directed sets, what kind of directed sets are there, and before moving ahead, two more important things are there. One is the residual subset of a directed set, and then cofinal subset of a directed set. So let us see these two definitions, what these are. So first of all is residual subset of a directed set D. So let D with this binary operation greater than or equal to, or you can say follows, let D greater than or equal to be a directed set, be a directed set, then a subset E of D, then a subset E of D is said to be a residual subset of D if there exists A naught in D such that for every A greater than or equal to A naught, your A belongs to E. That means after a particular stage, each and every element of D belongs to E, then E is said to be a residual subset of D. And then there is another definition, cofinal subset of D. So let us see what is cofinal subset of a directed set D. So I am not writing it once again because I will just change it here and you will get to know what is cofinal subset of a directed set. So let D greater than or equal to be a directed set, then a subset E of D is said to be cofinal, subset of D if, and after if the condition is going to be changed, if for every A belonging to D, there exists some B belonging to D such that B follows A and this B belongs to E. That means you take any element of D, there will be an element in D which follows that particular element and that element belongs to the set E. Then E will be called cofinal subset of D. If these two things are not clear by definition, then these will be more and more clear by the examples that are following these two definitions. So I am giving examples to clarify this concept of residual subset and cofinal subset of a directed set. So we know very well that N with greater than or equal to, this is a directed set, that is very well known to us. And now I am taking a subset E of N by N and delete from N 1, 2, 3, 5, 7. So let it be the set E. Then this set E is a residual subset of N because there exists 8 in the set of natural numbers such that for every A that follows 8, for every A greater than or equal to 8, this A belongs to the set E. Because E does not contain 1, 2, 3, 5, 7, otherwise it contains all the other natural numbers. So what are the members of E? These are 4, 6, and then every element after 8. So this is your E. So after 8, if you take this 8, then for every A greater than or equal to 8, 9 greater than or equal to 8, then 9 belongs to E. 10 is greater than or equal to 8, so 10 belongs to E. 11 is greater than or equal to 8, so 11 belongs to E. So there is a stage 8 such that after 8, every element is belonging to E. So that means E is a residual subset of B. And now, let us have another subset of N to understand the concept of cofinal subset of a directed set. So I am making this time E as the set of all you can say odd numbers, you can take all even numbers, you can take all prime numbers, you can take all composite numbers. So I am taking all odd numbers 1, 3, 5, 7, 9, 11 and so on. This E is cofinal subset of D because you take any element from D, because for every n belonging to D, there exists m is equal to 2n plus 1 belonging to D such that this m belongs to E. You take any n, you take 100, then 200 plus 1. It is also an element of D, but it also belongs to E, because E contains all the odd numbers. 201 is also odd number. You take your n to be 1 million. Then what is m? That is 2 million plus 1. That is 2 million 1. And 2 million 1 is an odd number. So it must belong to E. So whatever element you take here in D, 2n plus 1 will be the element of D that will belong to E. And that makes E your cofinal subset of D. So there are two concepts: residual subset of a directed set and cofinal subset of a directed set. Residual means after there will be a stage such that after that stage each and every element of set D will be in E. And cofinal means you take any element of D, there will be an element that will follow that element and that element will belong to E. So these are the two basic definitions: a residual subset of a directed set and cofinal subset of a directed set. And now slowly basically I am moving towards the definition of net. What is a net? How will we define it? But before moving on to nets, let us have a clear-cut concept about the sequences. What are sequences? It will help you to understand nets more and more clearly. So let us see what is a sequence. Normally we define a sequence like this or like this, but what it is? Actually, a sequence is a function whose domain is the set of natural numbers. So what is a sequence? Suppose you define a function f from the set of natural numbers to the set of real numbers. Define f from this as f of n is equal to n upon 2n plus 1. Here this function is having n, the set of natural numbers, as the domain set. So this is a sequence. It is not looking like a sequence. Why? Because we are habitual of using a different type of notation. Let us approach from this definition to your conventional approach, your conventional definition, your conventional notation. Normally we denote the function by f. Let me denote this function f by x. So what will be here? You will have x of n. So x of n is also a notation. So if I write this x of n, we change this notation to xn. X is a function from natural numbers to the set of real numbers, such that x of n, xn means x of n is n upon n plus 1. Now it is looking like a real sequence because you are habitual of using this type of notation. So this is a sequence. Now if nth term is this here x of 1 means first term x1, x of 2 means x2 the second term, x of 3 means the third term x3, and so on. X of n means the nth term xn. So this is your xn, the nth term of the sequence. So this is your sequence. So basically what is a sequence? A sequence is a function with your domain as the set of natural numbers. And now try to understand the definition of a net. What is a net? A net is a function with domain as a directed set. Now it is a directed set. Earlier it was the set of natural numbers. When I was defining sequence, I was saying that sequence is a function with domain as a set of natural numbers, and now net is also a function with domain as a directed set. That means sequences are a particular case of nets, because here we are using domain as a directed set, and the set of natural numbers is also a directed set. So that means every sequence is also a net, but every net need not be a sequence. We will give some examples to understand, to clarify this concept more clearly. So for example, your R with greater than or equal to is also a directed set. You define f from R to R as f of R is equal to R, or f of R you can say fr. Like we like xn, you like fr. So this fr is equal to R. This is a net, but this is not a sequence, because the set of domain set is not the set of natural numbers. It is the set of real numbers, and the set of real numbers with greater than or equal to in its usual sense is also a directed set. So this will be a net. This is not a sequence. Another basic difference between the set sequence and nets is that a sequence contains infinitely many terms, which is not a case that is necessary in case of nets, because a net may have a finite number of terms also. I am giving an example here, that define f. First of all, let x be a non-empty set. Moreover, let x be finite. Let x be a non-empty finite set. Then power set of x with subset of binary operation is a directed set. And define a function f from power set of x to R as f of a, because a is a member of power set of x. Members of power set of x are subsets of x. So a is a subset of x. So define f of a as order of a. That means number of elements in a. Order of a means number of elements of a. That means if you want to have this set, suppose a, b, d. So f of this will be 3, because number of elements here is 3. So order of this set is 3. So f of a is order of a is 3. So I have defined this function like this. This function is also a net, because this px along with this subset of is a directed set. We have proved in our previous video. So this function, where domain set is the directed set, is a net, but it is not a sequence. First of all, the domain is not the set of natural numbers. So why it is not a sequence? It is only a net. Secondly, x is finite. So power set of x is also finite. That means domain is a finite set. That means this net will have only a finite number of members. So the second basic difference between nets and sequence is that a sequence is always having infinitely many terms, whereas a net can have a finite number of members. So here we have given two examples of nets which are not sequences, but every sequence is also a net. That is to be kept in mind. Then there are three things to understand the convergence of net, the cluster points of net, the limit points of net. Three basic things are to be necessary to understand. Actually, f from D to X is a net where D is a directed set with some binary operation greater than or equal to. In some books you will get the notation that f dx greater than or equal to is a net. That means f is a function from the directed set to the set X, where this is the binary operation of the directed set. So this is the notation for a net. Or sometimes it is just written that f is a net. So it is understood that its domain is a directed set with some binary operation and there will be some range. So this is the notation, and now I am moving on to three basic definitions. The first one is if f is from D to X and y is a subset of X, then f is said to be in Y. I am giving stress in Y. F is said to be in Y if f of A belongs to Y for every A belonging to D. That means here is your D domain set, here is your X, your codomain, f is the function from D to this, D is having a binary operation greater than or equal to. Here you are having a subset Y, and here suppose A, B, C, D, E, F, these are the members of D, then F will be in Y if image of each of the elements is in Y. Image of each element of D is in Y, then we will say that the sequence F is in Y. This is the first thing. Secondly, F is said to be eventually in Y. F is said to be eventually in Y. Now I am giving stress on eventually in Y. If F from D to X is a sequence and Y is a subset of X, then F is said to be eventually in Y if there exists A in D such that for every A naught greater than or equal to A, that means every A naught that follows A, your F A naught belongs to Y. So let us make it clear using the diagram. Once again, suppose here it is your D with greater than or equal to as binary operation, here it is your X, F is your net from D to X, net means function, domain as D, and here some subset Y is there of X, members of D are A, B, C, D, E, F and so on. So what the definition says, there is some element in D, suppose the element is E. Here I am taking these elements in order. That means B follows A, C follows B, D follows C, E follows D, F follows E. That means they are in increasing order, like 1, 2, 3, 4, 5, 6 and so on. That means your F is greater than or equal to E is greater than or equal to D is greater than or equal to C is greater than or equal to B is greater than or equal to A. So they are in a particular order. So there must exist one element D such that now for every A naught greater than or equal to D. So what A naughts are now greater than or equal to D? All those that follows D. So that means this set. This is the set. And image of each of these belongs to Y. So image of D is in Y, image of E is in Y, image of F is in Y. These images before D, they may not be in Y. They may be in X, but they may not be in Y. But there will be a stage such that after that stage, image of each element will be in Y, and then we will say that our net F is eventually in Y. So this is the second thing. And now I am moving on to the third important thing. The third important thing is net is, once again, F from D to X is a net. D is having some binary relation greater than or equal to. Y is a subset of X. Then F is said to be frequently in Y if for every A belonging to D there exists some B belonging to D such that B follows A and FB belongs to Y. So what diagrammatically we can see it like, once again, it is D greater than or equal to, it is X, F is the net from D to X, and here is the subset Y. Here A, B, C, D and so on, H, I, J, K and so on. So what is the definition that the net is frequently in Y? So whatever A you take in D, suppose you take B, then there will be at least one element, suppose D, whose image will be in Y. If you take some other element here in D, there will be one element, say H, whose image will be in Y. You take any other element here in D, there will be at least one element that follows that element and its image will be in Y. And in such a case, we will say that our net F is frequently in Y. So three things. First of all, what is a net? Secondly, what is the basic difference between net and sequence? And thirdly, if Y is a subset of X, when will be F in Y? When will be F eventually in Y? When will be F frequently in Y? These are the things we have understood in this video. And I am going to stop this video here. In the next video, we will try to understand the limit points of a net, the cluster points of a net, and so on. Till then, thank you. Thank you once again.